So we only have 2 meetings left, really. Today's and
Wednesdays.
Wednesdays, 2 meetings. So next Wednesday. Monday is a holiday. So that takes out a big chunk. So, the plan is to move right on to chapter 27 of the classical mechanics text. And I have given you all the notes already. I don't think we can finish it, but we'll try to hit on the big points, the main points that are useful in physics applications at least. And we'll see how far we can go. As far as the problem sets are concerned, I think the last one I gave you was chapter 41 out of the quantum mechanics text. That's an important set of exercises, so try to go through them. That chapter is kind of like a hash over of some of the things in here that we're going to be talking about in more detail. But the exercises in there are still useful. I will try to work out a few of these exercises in chapter 27. I haven't done so yet. Since we are not covering the whole chapter, I'll try to decide on which ones are the most important problems. There's a whole bunch that I've marked down in this chapter, in fact. And I know that definitely we cannot cover them all, so we'll see. Okay? There's like 12 problems in this chapter. But 13. 15, actually. So we'll see. Okay? So I'll give you the final. Well, I have given you all the notes already. And I'll give you probably by early next week, the rest of the solutions to the homework problems. And as we all know, the final exam is actually, because of the bad mistake I made, unfortunately, it's on a Monday, okay? It's a Monday, the first day of the final exam week. It's going to be 1:40 p.m. to 3:40 p.m. And it will be pretty much the same style of a test. I'll give you most kind of questions on testing you on conceptual understanding of various things with a couple of small calculations. Okay? Pretty much like a midterms 1 and 2. Sort of.
Is it going to be cumulative?
Or it's going to be cumulative. Probably with some emphasis on the latter parts. Slight emphasis on the latter parts. Okay. So let's do Riemannian geometry and Riemannian curvature. Or basically focus on what's called a Riemann curvature tensor, which, as you know, is of prime importance in general relativity, but in a different guise, it's of prime importance, not the Riemann curvature tensor, but the general curvature tensor is of prime importance in the so-called gauge field theories in elementary particle physics. All kinds of gauge fields, electromagnetic field, strong interaction, electroweak, and so on and so forth. Okay, so-called Yang-Mills theories. So, let us focus on Riemannian geometry. And Riemannian geometry is, of course, defined on the basis of a given Riemannian metric, which we've seen this many times, is a rank 0,2 tensor, covariant tensor. Oh, Ian.
Great, thank you.
Rank 2 covariant tensor, and in general it depends on the position, so let me just write this explicitly. If the space is of n dimensions, then locally a point can be characterized by n coordinates. And it's given like this, that the square of the infinitesimal arc length, called ds squared, dxi, dxj, okay? Now, this is what is called a two form, but not an exterior form, in the sense that mathematically you kind of write it like this with the direct product in here, which means that just slap two things together. There's no anti-symmetry properties to it. But we do require a couple of properties for the Gij. The Gij is required to be symmetric matrix, and also it's required to be a non-degenerate matrix, which means that there exists an inverse to the matrix. Okay, so the only two conditions that the Riemannian metric tensor needs to satisfy, so-called metric tensor, is to satisfy symmetry. So Gij is equal to Gji, and then second, as a matrix, determinant Gij is not equal to 0, which means that there has to be an inverse. Okay, and you can state in a couple other ways also, but probably this is very direct. Okay, more direct. And everything else would follow from this given Gij. So the particular properties of a particular geometry, a Riemannian geometry, would then depend on what Gij is. So and we'll see how it unfolds from here. The various things about curvature and covariant derivatives of vectors and so on and so forth, and we'll see how it kind of follows from here. Now, let us then retreat, take a couple of steps back, and first just look at what's called a tangent bundle of a manifold, even before the Riemannian metric is given. Okay, so you can take a look at some n-dimensional differentiable manifold M, and let's consider the tangent bundle. That means bundling together in the sense that we have talked about last time, from the abstract vector bundle to a tangent bundle. And so this is usually written just TM, tangent bundle. I mean, slapping together the various tangent spaces at each point, and in such a way that the given properties, the stated definition last time for the vector bundle applies. Okay, this is called a tangent bundle, but we can loosely think of it as tangent spaces slapped together at each and every point of the manifold. So there's one tangent space at each point, and so of course at this stage there's no canonical relationship, so to speak, between the different tangent spaces, because they are, even though structurally they are the same. Each one is an n-dimensional vector space, but we haven't put in any relationship between the vectors in each space. Okay, until of course you put in what's called a connection, and the connection is used to differentiate vector fields, or sections as we call them from the last chapter, until we put in a connection which will then serve to connect the various vectors in the different vector spaces that are the tangent spaces. A connection on a tangent bundle is what's called an affine connection. Okay, so it's the first term that we know. Affine connection is any, so there are many different kinds of affine connections. Okay, it's any connection introduced on the tangent bundle. Okay. Now, you know that you can specify the connection by means of a matrix of one forms. That's called a connection matrix. And the idea is, supposing that you choose a basis, it doesn't even have to be an orthonormal basis at this point, okay? Which means you've chosen a frame, and you choose a frame at each tangent space. So you choose one particular frame at each tangent space in a smooth way. That's called a tangent. That's called a frame field. Okay, it's called a frame field. After having chosen a frame field, let's say that the frame field just then written in this manner. We're talking about the general n-dimensional case. Okay. So E1, E2. Okay, E1, E2 for the case of a two-dimensional tangent spaces. And then you specify the connection by means of this relationship where the J is summed over. Okay? And of course, you can view this as a matrix where the lower index here is the row index and the top index is the column index. You can view it the other way also, but then you need to be careful. Certain formulas will appear to be different. So let's stick to a convention, and this is what we are going to do. We have been doing that all the way through in this course and in the classical mechanics course also. Okay? So for example, omega ij, you can write it as omega 1, 1, omega 1, 2, and so on and so forth. Omega 2, 1, so this is omega 1, n, okay, and so on and so forth. Okay, so the lower index is a row index and the up index is the column index. Now, because this is supposed to be a small change, that each of the matrix elements is a differential one form. Each of the matrix elements is a differential one form. And so each one of them is going to be a linear superposition of all the dx's, okay? And so there has to be a symbol in here which depend on x, will depend on k, so the k is summed over, this is up, then there must be, the k index must be down, but then it must reflect these two indices also. So the index structure is like this, you stick in a symbol for that. That's what usually what's called the Christoffel symbol, as you well know, okay? So in general, then, as I asked you in the test, if you're dealing with a space of n dimensions, a tangent bundle, the base space has a dimension n, then there are three indices. Each index is, can have n values, so they're n cube components, so to speak, for the Christoffel symbols, okay? N cube components. Many of them may be equal to 0, but in general, there are n cube components. Okay, this is a connection. And so far, we haven't said anything about the connection. Remember, all that a connection is required to do is to satisfy the two conditions that we wrote down last time, that if you have two sections, a section is it's like a vector field, okay? And so that you can perhaps write this as a linear superposition of the bases, okay, at each point, okay? And so if you want to differentiate this section in here, you would have this rule that this is equal to dsi ei. This is the exterior derivative plus si big dei, okay? And which is to say that this is equal to dsi ei plus si omega ij e, oops, yeah, sorry, si, and then omega ij ej like that. Okay, excuse me. And if you want to, you can put in the Christoffel symbols and so on and so forth. So this is one rule in here. In general, you can write it like this. If you have a section that's called S, and you have a number that's called let's say alpha, then the rule for the exterior derivative, covariant derivative is this: that this is equal to d exterior alpha S plus alpha cap S, like that. That's why, and the other rule is simply d of S1 plus S2 is equal to ds1 plus ds2, okay? So any operator, you see the operator d in here goes from the set of sections on the bundle E. Remember, E is called the total space. It projects onto the base manifold to the set of sections on cotangent bundle M cross with E like this. Written in this way, it's a bit abstract, but what the presence of this cotangent bundle is to take care of this presence of this thing in here, which is a first order differential which lies on the cotangent space. Okay? That. So any operator which, obviously this is a linear operator, which any operator satisfying these two rules is said to be a covariant derivative, and obviously there's in principle there can be an infinite number of connections, okay, that can be imposed on a particular vector bundle. And as I mentioned last time, the very basic theorem about a connection is that a connection always exists on a vector bundle. That's a basic theorem, so you can start talking about them, okay? Now, here comes sort of a subtlety in here. Connections are usually expressed locally, okay? When you write out the matrix elements in here, they are written out with respect to particular choice of coordinate system, and so on and so forth. And of course, they are written out with respect to a particular choice of basis vectors. When you go to a different set of basis vectors, then you have to do a so-called gauge transformation of the connection matrix, but you are still talking about the same connection. So any two forms of omega matrices which are related by a gauge transformation actually belongs to the same connection, okay? And then you can start talking about different connections, okay? And you have really a different connection. Any omega matrix from each one cannot be related to each other by a gauge transformation, okay? So there's this subtlety to think of, and that is because we have chosen a particular choice of frame field to express our connection matrix with, okay? Just like, in the case of a tensor, you have chosen a particular basis set to express your tensor components with. And similarly, you have chosen a particular basis to express the components of your Christoffel symbols with. The difference, of course, is that we don't call this a tensor, even though there are 3 indices in it. It doesn't transform one, okay? Because you recall that the relationship between general gauge transformation is this, that if you have two bases which are relatable by this, EI is GIJ, EJ, with GIJ, of course, is a transformation matrix. It transforms one basis set to another basis set. And you see that the field, the E's are a frame field, so you can have different choices of the GIJs at different places in the manifold, okay? So that the GIJs, when you change from one frame field to another, it is in general the case that the GIJs here, now remember this GIJ is not the metric, very different. This is just a transformation matrix, okay? Would usually depend on the position, okay? That's called a local gauge change, local gauge change. You only change it locally, okay? That's why the transformations depend upon where you are, okay? Depends upon the local coordinates. And then you recall that a very simple derivation shows that when you transform to writing the omega with respect to E, you transform the same connection when you try to write it with respect to the E prime. Then you get a new matrix omega prime, which is related to the old one by this formula in here. You will recall that dGg inverse plus G omega G inverse. That's a matrix equation. This is called a gauge transformation equation, okay? A very important one. You see, even though you started off with some zero thing in here, locally, locally a gauge, a connection can be transformed to zero. Locally, it can be nothing. But then, actually, elsewhere, it cannot be. If for a connection to be actually not the trivial connection, even if it appears to be zero somewhere, it will reappear as some non-zero thing elsewhere. Okay. So even if you have a zero here, then you usually have this term in here which may make it into a non-zero thing. So this makes it a non-tensorial transformation. Remember, tensorial transformation is always such that it's a linear transformation, so the zero tensor always gets transformed to a zero tensor. Okay, but this is not the case in here. That's the reason why we say that the connection is not a tensor. It's a connection. That's what it is. It's a connection. Okay. So, so these are very general things, right? So far, very general. But specific enough for us to continue to introduce the next important concept, which is the curvature. Okay. So while we write the specified connection matrix in this way. By the way, you can either regard this as a matrix of one forms or what is called a matrix valued one form. It's the same thing. I'll let you think about it a little bit, okay? But I find it a little bit easier to think of it as a matrix of one forms so that each of the matrix elements is a differential one form, okay? Okay. Next thing, we're going to introduce the so-called curvature. The connection is a one form, and the curvature is a two form. And we will show you how to generate the curvature, which is a two form, from the connection, which is one form, by a very simple formula. And this is really the key formula of a lot of physics. Let's say one of the most important mathematical formulas in physics, I guess. And this is this. So from the one form omega, we're going to get the two form. So we do this. You differentiate a one form, you get a two form. But this is not enough. You add in this thing in here. Well, I'll write down for you in detail what this means. This incorporates two kinds of products, a matrix multiplication as well as an exterior product. Okay? And so this is a one form, this is a one form. You exteriorly multiply them together, it becomes a two form. This is a two form, this is a two form. You add together two forms, you get another two form. This two form is called a curvature two form. As simple as that. As simple as that. Okay? Just as we express the omega like this, this is going to be a matrix of two forms. So the omega is a matrix of one forms. This is going to be a matrix of two forms, okay? And so we write the matrix like this, right? Omega ij. This is a two form, okay? Each of the omega ij's is a two form. Is d little omega ij. That's clear enough. So minus omega wedge omega ij, like so, okay? But remember, each of these guys is a matrix, okay? So you need to multiply these two things together as matrices. And what is the ijth element of the product of this? And it's very simple, which is simply omega I k wedge omega kj, like that. Okay? Bless you. So that's it. So that, you calculate the particular element of omega ij. And so you have little omega like that, so you have big omega like that, omega 1, 1, omega 1, 2, omega 1, n, omega n1, omega n2, omega nn. And each of these guys is a two form, is an exterior two form. Okay, differential form. It's an exterior differential two form, like that. Because this is a matrix in here, this is not necessarily zero, okay? If this were not a matrix, because this is an anti-symmetric product, then it would be zero, as is in the case of an abelian gauge field theory. You have seen that already in the electromagnetic case. It's an abelian theory. The gauge group is U1, so the omega is not really a matrix. It's a one-by-one matrix, so it's just one thing. So the second term goes away. Omega wedge omega goes away for an abelian gauge field theory, leaving only d omega for the curvature. And in that case, let me just recall a couple of things for you. for the abelian case, since it's not a matrix, there's no need to put the ij, okay? It's a 1, 1, there's only one thing in there. So we write this as ak, actually wait, this script ak dxk like that, okay? For the case of an abelian theory situation. And then you imagine doing the derivative of this, okay? Becomes a 2 form. And we write the 2 form as 1/2 fij dxi wedge dxj. Okay? Where the I and j are summed over in an unrestricted fashion. Now, because of the fact that the dx's are, this wedge is an anti-symmetric product, right? And so if it runs unrestricted, there would seem to be n squared combinations of these things, right? But of course, because this is anti-symmetric, so you knock off the diagonals already, okay? And then you have just knock off the diagonals, all zeros. And then you're just left with these ones, okay? Because these ones would be negatives of those ones, that's all. So how many independent elements are there? Really? Huh? Well, actually not quite like that. It's not quite like that. Let's just take 3, where each of I and j can go from 1 to 3, okay? So that's right. In that case, you have 0, 0, 0. You have 1, 1, 1, 1, 1, 2, 1, 3, 2, 3, and that's that. Okay? You have 3 independent ones. But this is really equal to the number of ways that you can choose 2 things out of 3 things. Right? So this is equal to 3 factorial, 2 factorial, 1 factorial, and this is equal to 3 things, okay? But what if I have a 4-dimensional situation? If I have a 4-dimensional situation, it would be 4, 2, right? And so on, and so forth. Why? Because you really just need the distinct combinations, okay? But this is different from that. Because if the order were otherwise, then one would be the negatives of one of the other ones, that's all, okay? So there are really only so many independent elements when you try to sum this over, all right? And in the case of an n-dimensional, a 2 form, in the case of an n-dimensional, you would just have that many elements, okay? Actually, this is equal, this is equal to that situation, because this would be equal to n factorial, 2 factorial, and minus 2 factorial. Would be equal to n times n minus 1 divided by 2, which is equal to n squared minus n divided by 2, okay? But if you talk about it in general, an R form, you have xi1 wedge xi r, an R form, all of these guys, okay? And if each of the i's can range from 1 to n, then how many independent elements would there be? Would be n factorial r, okay? Like that. So in this case, this is a 2 form in here, and there would really be just this many linearly independent elements. And so instead of writing this as an unrestricted sum, which really overcounts, you see, you could just define something that is summed over I and j, but always letting I to be less than j. That would be one way of doing it. Okay, always letting I to be less than j. But if you write that as an unrestricted sum, and there would be certain advantages to doing that, you always stick in a half to kind of deal with the overcounting, so to speak. And you can easily verify that at home, okay, why you need to write the 1/2. I think we have mentioned that already at an earlier time. And in this particular case, if you differentiate this, you see that gamma ij is just diaj minus dj ai, like so, doing the exterior derivative. Yeah?
So the F is just digamma, right?
Huh?
The F is digamma?
Di.
The F? Is that right?
The F is called a curvature tensor, actually.
Okay.
I'm sorry, what did you mean to say?
He said that he asked if the character that you use for the tensor is digamma, but it's just F.
What is a digamma? Anyway, it's not whatever you're thinking of. It's just an F. Okay. All right. It's a symbol. It's a symbol that's traditionally used for in the physics literature, at least. Okay. But clearly, you see, when you deal with the non-abelian case in here, there would have to be two other indices in here also, and the situation becomes a bit more complicated. Okay. And so, in other words, instead of just dealing with this term, you would have to have this term also, which makes the theory kind of, at this early stage, a nonlinear thing. You have two of these things in here, two of omegas in here, okay? And I think that's a basic reason for the nonlinear nature of the equations of motion for a non-abelian gauge field theory, such as the gravitational force and some of the other things, the strong forces and whatever, and so on and so forth. The equations are much more difficult to solve because it's nonlinear in the gauge potentials, okay? Instead of the electromagnetism, which is a linear theory, the equations are always linear in the gauge fields, okay? Okay, so let me immediately prove a couple of things. Even though omega is not a tensor because it transforms like this, little omega is not a tensor because it's a connection with big omega is a tensor because it transforms like a tensor. And in fact, if we do this kind of, if we do this kind of a gauge change of frame fields, which is essentially a gauge transformation, you'll see that that's the first thing we're going to prove, that with respect to the prime faces, omega prime is equal to G omega G inverse, essentially, as a matrix, okay? So 0 transforms into 0. 0 curvature in one frame transforms into 0 curvature in the other frame. You see the difference in the transformation properties between the two, okay? In this thing in here, there's this extra, oh, is this blocking? But that's the best I can do. I don't know I can.
That's good.
Okay. So compare this, okay? Compare these two, and they're very different. The big omega, the curvature two form, is a tensor, okay? Transforms like a tensor, but the connection is not a tensor because it does not transform like a tensor, okay? It would have to transform like that if it were a tensor. So let's immediately prove that. The proof is actually very simple. And so we rewrite the this gauge transformation law in this way. We multiply by G on the right in that equation, okay? Multiply by G on the right. So I've got omega prime G is equal to dg plus G omega, okay? Then we do this. Exteriorly differentiate. Like so. Now, at this point, I need to remind you of one very important rule of exterior differentiation, the product rule for exterior differentiation, okay, which goes like this. Supposing you have two differential forms, omega 1 and omega 2, and they can be of different orders, okay? So if this is like an R form, this is like an S form, let's say, okay? Then you can certainly wedge them together to get an R plus S differential form, okay? And supposing you want to exteriorly differentiate it, then you get an r plus s plus 1 differential form, okay? And now, an ordinary product rule would prompt you to write something like this. That would be how an ordinary product rule works, okay? But because of the anti-symmetry properties of the exterior product, you have to stick in a factor in here that is minus 1 raised to some power. What is the power? The power is the order of the first one, like so. It makes a difference because the order makes a difference in here because these things are anti-symmetric. The exterior product is anti-symmetric. It doesn't matter what the order of the second one is, okay? If you write it in this way, this is the basic formula, all right? And one of the exercises in chapter 41 asks you to prove this using the local expression for an exterior derivative, which I have given to you. And you should go through that and understand very carefully why this is true, okay? Now, perhaps another formula, this time it's not even concerning exterior derivative, but the anti-symmetry rule for an exterior product goes like this. Supposing I write omega 1 wedge omega 2, let's say this is an R form, this is like an S form in here. What's the relationship between this and omega 2 wedge omega 1? Certainly it's not equal to each other, okay? But this time, again, you have to multiply by a factor which is minus 1 raised to some power. What is the power? The power is the product of these two orders in here, like so. You should also prove that, okay? The solution is given to you also, one of the exercises in chapter 41 of the quantum mechanics test, okay? So always make use of these two rules, all right? So these are, besides the one that gives you, if you write omega as, let's say this is an R form, so it's AI1 IR dxI1 wedge dxIR, where there's a sum in here, right? And then the rule for d omega is what? Is partial AI1 IR dj dxj dxj. This has to go first, and then wedge with all the rest of them. I think with these formulas you can almost go anywhere, okay, with dealing with exterior derivatives. And certainly you can prove both of, you can prove this product rule of differentiation using this local formula for the, actually how to calculate the exterior differentiations, okay? So let's put these aside. And now let's go back to here. Oh, there's another rule which can be proven using this also. D squared is always equal to 0. That's a very useful one. You do it twice, you kill it, okay? Just remember, you do it twice, you kill it, okay? Okay, so that kills this first term, okay? Because, you know, no matter what it's operating on, D squared is equal to 0, okay? So this term goes away. And now we use the product rule for exterior differentiation on this first thing in here, okay? Now, G is actually not a one form because G is like a function. G is a matrix, but each of the matrix elements is a 0 form, so to speak, okay? So actually you can write G before or after omega prime. It really doesn't matter. But let's write it the way it is now. Let omega 1 be omega prime and omega 2 be G, only that now the second one is a 0 form, that's all, okay? And so on the left-hand side, what do you have? You have, oh, you know why? The order makes a difference. The order makes a difference because these are matrices. I forgot. The order makes a difference because these are matrices. Okay, so you have to write it like that. Otherwise, you would get into trouble. So just remember that when you try to do this on a high level, so everything is a matrix equation, you have to remember that the matrices involved also. Okay. But this is a 1 form, this is a 0 form, so we write this left-hand side as d omega prime wedge with g. Let's just write it like that, okay? Actually, this is a 0 form, so I don't really have to write the wedge product, so I can just write it like this. Plus minus 1 raised to the what power? R is equal to 1, right? Minus 1 raised to the 1 omega prime wedge with dg. Now you have to introduce a wedge. Why? Because dg becomes a 1 form now. G is a 0 form, so dg is a 1 form. So here omega prime is a 1 form, so you have to wedging together two 1 forms, so you need to put in the wedge product. Okay? Does everybody see that? So this is just like a minus 1 raised to the first power. It's just a minus in here. Like so. So this is the left-hand side. The right-hand side, we do the same thing. Okay? Again, in that order, this is 0 form. This is a 1 form in here. All right? And so you write this as dg wedge with omega. This time is plus minus 1 raised to the 0, which is a plus 1. So it's a plus sign in here. G d omega. Okay, you don't need to put a wedge sign because G is a 0 form. Okay? Okay. Now, this equation also gives, now let me put in the original equation which we started with. Omega prime G is equal to dg plus g omega, right? Which comes from that. So this equation gives dg is equal to omega prime g minus g omega. All right. So we stick that result into here, where we see a dg. We stick that result in. So I then have d omega prime times g minus omega prime wedge with omega prime g minus g omega. That takes care of this term in here. Is equal to dg is omega prime g minus g omega wedge with omega plus g d omega. All right, very straightforward, okay? Very straightforward. Okay, which, let's see what we do. So this becomes d omega g minus omega wedge. So let's just write these first two terms, right? So write these first two terms as d omega prime minus omega prime wedge with omega prime times g. Is that all right? So that takes care of those two terms, okay? And then I have what? And then I have minus. A minus and minus is a plus in here. Okay? So it's omega prime wedge with g omega. Okay? Going over to the right-hand side, oh, I have the same thing. Omega prime wedge with g omega for the first term. That takes care of this term, okay? And then I have plus g times d omega minus omega wedge omega. You see that? Okay? And of course, these two are the same, so I cancel that out from both sides of the equation. And so I have it. This is what, by definition? Big omega prime. You see, omega is always defined like that, right? So if the little omegas are primes, the big omegas are prime also. Okay. So then we end up with taking this equation, right? This bottom equation, and I have big omega prime G is equal to G times big omega, and that's it. Okay? And of course, that leads us to that equation over there. So omega prime is G big omega G inverse. So the big omega transforms like a tensor. Yeah.
Did that how Catan found the big omega?
Catan wrote down that equation. He probably immediately saw that this is true. Okay? Catan wrote down that equation, but the major contribution is that, before that time, general relativity was kind of separated from all the rest of physics, and people wrote down all those, Riemann curvature tensor equations and so on and so forth. They did not have a general definition for the curvature of a vector bundle. Catan realized that instead of tensor bundles, tangent bundles, you could have many other kinds of vector bundles also. And so he proceeded to try to derive an expression for the general curvature for a general vector bundle instead of just a tangent bundle. Okay? And then they came upon this. So this is a major thing, even though it appears to be rather simple at this point. It's a major generalization, okay, so to speak. Okay. Okay, there is another very important relationship that the big omega satisfies, and that's called the Bianchi. There are two Bianchi identities. I think this is either called the first Bianchi identity or the second Bianchi identity. I forgot. But this one is very important because this leads to two of the Maxwell's four equations. So two of the four Maxwell's equations, the ones which do not involve any sources, del dot B is equal to 0, and the other one is Faraday's law, which del cross E is equal to minus dP dt. Those don't involve any sources. Those are entirely geometrical in character, okay? And the other two involve sources. So, I mean, as physics equations, some of those would have to involve sources. The other two involve charge densities and current densities, right? Del dot E is equal to charge density, and the other one is what? Del cross B is equal to current. That's the last of Maxwell's equations, which relates the displacement, to J and so on and so forth. Okay, so let's see what the Bianchi identity is. Let me just simply call it the Bianchi identity at this point, which is if you take the omega 2 form, you d it, you get a 3 form. And this 3 form on the right-hand side looks like this in general. The two do not commute for non-abelian theories, and they do commute for abelian theories. So for the electrodynamics, it's just that d big omega is equal to 0. Okay, d big omega is equal to 0. As I said, involves it gives you two of the four Maxwell's equations. Del dot B is equal to 0, and del cross E is equal to minus dP dt. Okay. Okay, let's prove that. Okay. And so you start off from omega is equal to d omega minus omega wedge omega, and you calculate d omega like that. And so this is equal to d square omega, which automatically goes to 0, minus d of omega wedge omega, which is not 0 if little omega is a matrix. Okay. And making use of the product rule again, we have d omega wedge omega minus, right? There's a minus sign because each of these is a one form, minus omega wedge d omega, like so. Okay. And we are simply going to write d omega as this implies d omega is equal to big omega plus omega wedge omega like that. Okay? And so instead of d little omega, I put a big omega plus omega wedge omega wedge omega. Let's see. Okay, d omega is equal to omega plus omega wedge omega minus omega wedge omega plus omega wedge omega. Seem to have made a mistake in sign. Oh, there's a minus sign. Oops, there's a minus sign in here. Okay, so this is a minus, this is a plus. So this is a minus, this is a plus, like that. And of course, there's this term in here which is minus omega wedge omega wedge omega, and there's this plus omega wedge omega wedge omega. So those two go away. Okay, and leaving us only with this thing in here. Okay, so that's called the Bianchi identity. This is the Bianchi identity, again, in any general Yang-Mills equation, those two play very important roles. Okay, the Yang-Mills equations for non-abelian cases are just generalizations of Maxwell's equations. Okay, even though they are nonlinear, they're still generalizations. And as you can see, there's always a purely geometrical component to those field equations, which purely comes from the definition of the curvature. The other ones would have to involve sources in the physical situation, whatever those sources are. Okay, mass, energy, momentum, blah blah blah, things and so on and so forth. Okay, charges. Okay.
What's the physical meaning of the omega? Omega is,
Big omega curvature.
well, of d omega.
D omega. D omega, okay, here's a physical, so if it's globally true that, that d omega is equal to omega wedge omega, in other words, this is zero, then the curvature is zero everywhere, okay? So this equation means that there's no curvature corresponding to this particular connection. Okay? This actually is called, this equation, you know, the general equation, when a curvature is not zero, is known as one of the so-called Cardan's structure equations for a particular fiber bundle. Okay? Yeah?
Right, but he asked what the physical interpretation of d omega is.
D of little omega, right?
No, d big omega.
D big omega. Oh. I think, well, you can kind of tack on a physical interpretation by trying to apply this Bianchi identity to the various physics problems, such as electromagnetic field and so on and so forth. Okay, so in the abelian case, you have d omega is equal to 0. Then you can ask what's the physical significance of this thing in here. Now omega itself is a field tensor, right? Omega itself is a field tensor. So this says a derivative of the field tensor is equal to 0. Some derivatives of the field tensor is equal to 0. So that when you think about the electric and magnetic fields, it would be some derivatives of those are equal to 0. For the B case, it's now for the electromagnetic field, because it's really Lorentz invariant, the field tensor is an anti-symmetric tensor. Okay, and I don't remember exactly how these three are the B fields. There's a minus sign somewhere. Can you remind me? These one are the E1, E2, E3. Okay. These 6 things are the various components of of omega, when you put omega is equal to 1/2 Fij dxi dxj. So there are those 6 things, okay? There are those 6 things when actually in the relativistic case we write this as mu nu. In the physics literature, mu nu is for space-time, okay? Ij is for just like that, okay? There are these 6 things, and you can calculate the d in here, and then actually substitute that, when you have identified the components, and then you can get these 2 equations. You can get these 2 equations. So what is the physical significance of d omega? It's a various space-time derivatives of the field tensor. Okay? And the fact that they have to be connected in certain ways, that they're not all independent precisely because of the Bianchi identity, whether in this more general form or in this more restricted form, like that in here. The derivatives are not independent of each other. Okay? There's a time derivative that's connected to a space derivative, and so on and so forth. Okay? Does that help? Okay. Okay. Next, I want to move on to the tangent, the affine connection now. And actually, we're the place where we can define the Riemann curvature tensor now. Okay, we're the place where we can define the Riemann curvature tensor. Let's take a break first. Okay, good time to break. Riemann curvature tensor. So omega ij is gamma ij k. These guys are functions of all the coordinates dxk. So let's calculate the ijth element of the curvature matrix of 2 forms. D omega ij minus omega ik wedge with omega kj. And remember this product omega wedge omega is a matrix product also, in addition to an exterior product of differential forms. And now if we do it straightforwardly using this result in here, then you know how to differentiate this thing in here. You would simply write partial gamma ijk d. I have to introduce an extra index in here. Let me call it the lth one. And so dxl. And I've wedged this together with all the other things that's already there. But the only other thing that's there is dxk. Okay? So this is the first term. Okay? And the second term produces, again, according to using this equation, omega ij is, we're going to write it like this. Omega ik is gamma, let me see. Kj. Let me write it. I. There's a summation in here, and let's see. dl dk. For omega ik, I'm going to write. See, for some reason, I write it like. L. Oh, there's a summation in here. So, for some reason, I've chosen to call this by a different name. I've chosen to call this H in the notes. Okay. Because I've used the K here already, so I have to be careful. Okay. So this is gamma I H L, let's say, dxl, and then wedge. Now the gammas are just numbers, so I can multiply them together. Hj, let me call this one k, and then dxk. Are you comfortable with that so far? Okay. That's how you use the indices, okay? Now, remember what I wanted to do is to define omega ij to be, want to define this, in this step I define what's called the Riemann curvature tensor. I have 1/2 R for Riemann, and there's ij in here for this ij. Since it's a two form, I have to have KL, like so. dxk wedge dxl. I define the Riemann curvature tensor like that, which is a 4-index object like that, okay? Where the k and l are summed over there, so leaving only indices I and j. I is in low position, j is in the upper position, okay? I define like that. So obviously then I would like to relate the Riemann curvature tensor as we have defined here to these things in here. Okay? Well, first of all, I have to bring out a factor 1/2 because I want to write this as an unrestricted sum in that sum over there. Okay? So write 1/2 means really it's 1/2 of this plus another 1/2 of this. Okay? So here we go. Is equal to 1/2. So the first half is, write this in terms of dxk wedge dxl. For some reason, because it's in this order right here, okay? I want to write this in terms of dxk wedge dxl because I want to compare it with this object over there. But this is LK. So if I want to change it in the KL, see L and K are summed over in here, so I could write the L as K and K as L in this first half. Doesn't matter, okay? So if in this business in here, I write the K as L and L as K, this is what I end up. J, I, L, dxk, all right, plus, right here, I write the k as L. Let me see what I want to do. Minus IHK. Okay, here I write the k as L and L as k. Let me do that carefully, right? If I write the k as L and L as k, I get gamma I H K, gamma H J L D X K wedge DXL. IHK HJL. Okay? So let me put it here. Okay? So I have minus gamma IHK IHK gamma HJL. That's one half of it. Okay? Now there's the other half. Okay? The other half, I'm simply going to switch the K and L in here, giving me minus dk wedge dl, and so I have a minus, the same thing over here, right? D gamma I j k dxl. All right? Now for this term, what I want to do is I switch this dxk and dxl, And so that gives me a minus. This thing now becomes minus gamma I H L gamma H J K dxk wedge dxl. Is that okay? But there's a minus sign there already, so it becomes a plus, okay? So this is a plus gamma IHL gamma HJK. Yeah.
Are you just writing out every single term that has a dxk wedge dxl?
Yeah. Because the L and K are summed over, all right? I'm simply saying that this thing is equal to 1/2 of this plus 1/2 of itself, okay? The first half I write in a certain way, the second half I write it in a certain way. All right? Now go home and verify this. Sometimes it causes it to pull your hair, but that's the way it is. So I finally get this remarkable formula, which you can find in your general relativity text. The Riemann curvature tensor, Rijkl, for index thing is, first of all, there are two partial derivatives. And then there's a difference between two gamma terms. It's up to you to figure out a way to remember how to stick in the indices. First of all, the KL is, first of all, this is IJ. So the I has to be in the lower place and J is in the upper place. So here's IJ, okay? And here's also IJ. So dx, dx. So one is K, one is L, okay? So this is L. You put this L in there. This is K. This is K. This is L like that. So that's the first two, okay? And here, there's obviously a sum. The sum, so the H has to go down here. Also, H, and the J has to be on top. So it's like that. IJ, that's KL. So K either goes here or here, and the L goes in the other place. The first term is when L goes here, and K going here, okay? And the second term is kind of like a similar thing, I, J, okay? And there's a sum over H, H in here. And obviously, if this is an L here, this is K here, this K here, this is an L here, like so. It's called a Riemann curvature tensor.
So in consideration of this piece, do we get a note card for this?
You can bring 10 note cards to write this down. I can't remember this myself. Okay. All right. But that's an important formula because this is the formula which allows you to, if you knew the connection, that means you know the Christoffel symbols. And there's a way to calculate the Christoffel symbols for a particular kind of connection. Given the metric tensor, we can find a very special connection that is called a Levi-Civita connection that can be, so that would allow us to calculate the Christoffel symbols in terms of the tensor, metric tensor elements, derivatives of metric tensor elements. Once you calculate the Christoffel symbols, then you can use this formula to figure out the Riemann curvature tensor.
And you tested this on this in first quarter classical?
In where?
First quarter classical where you had us derive it.
Did I?
Yes.
No, I did not give you this. No. Did I? No. Which first quarter classical?
Yeah.
No, I didn't. You have to show me. Did we test you?
Remember that basic required classical?
If I did, I gave you the equation. I didn't ask you to.
Yes.
Yeah, if I did, I gave you the equation. So it's a matter of plugging in. Okay. Now you see where how it comes.
Yeah, it was just
For the torus?
no, it was just finding what the Christoffel.
Yeah, just finding what the
were,
Christoffel symbols were given the omegas. That's simple.
It was actually just plugging in.
Just plug it.
numbers.
Yeah. Just that took 2 minutes. One of the questions in the last midterm that took 2 minutes. But calculating That's when I gave you the omegas, right? When I gave you the omegas, asked you to calculate the gammas, it's just a matter of reading it off, okay? There's no calculations in there. But there's a neat formula which allows you to calculate the gammas corresponding to a particular connection called a Levi-Civita connection, which are calculated in terms of the metric tensor elements or derivatives of them. That's much more difficult. You have to do a bunch of derivatives and so on and so forth. That's when you do in general relativity, okay? Where the metric tensor elements are not zero, are not delta functions, are not constant at least, okay? So that's why we say that both Euclidean space and Minkowski space are flat, because the metric tensor elements are constants all over the place, and so the Christoffel symbols are all zeros, because the derivatives of those metric tensor elements with respect to position coordinates are all zero, okay? Flat space, yeah?
I'm just wondering, how does the rank 4 tensor look written out? How would you write that?
You would have to write out in terms of big fat table, which has, you would have that many elements, right? In general, you would have that many elements, but the number of elements for the dimension 4 case is actually reduced because of certain symmetry properties. Okay, greatly reduced. What is that? 16 times 16, 256 or something like that. But I think there are only 10 independent elements or something like that, because of certain symmetry properties that we can derive pretty soon. Okay. Now we go to the metric tensor and see how to calculate the Christoffel symbols corresponding to a very unique connection that satisfies two very important properties, and that would allow us to calculate the Christoffel symbols in terms of the metric tensors. The two properties are metric compatibility and torsion freeness of the connection. I'll explain in detail what that means. Okay? There's a geometrical, pictorial interpretation, and there's also an analytical way of writing it down. The fundamental theorem in Riemannian geometry is that there's, among all the infinitely many connections that you can build on the tangent bundle, there's only a unique one which satisfies these two conditions. That one is called the Levi-Civita connection. And that's the one we are using in general relativity. Okay? So let's go back to the. We write the metric as a tensor. We write this as big G, and we simply write this as we wrote this already, Gij. So this is a differential form, but not an exterior differential form. So we don't use a wedge. We just use this ordinary cross dxi dxj, where of course the ij is to be summed over. So this is a two form, okay? This is a two form, but not an exterior form, because there's no symmetry or anti-symmetry to that. So D1 cross D2 would be different, totally independent of D2 cross D1, okay? But Gij itself, as we'll see, is a rank 2 tensor, is a rank 0-2 tensor. It's a covariant rank 2 tensor, as we'll demonstrate, okay? Now, so this immediately allows you to calculate. It's a rank 2. It's a true form, so therefore you can use it to act on two tangent vectors. Okay, and supposing I have two tangent vectors, x and y. Okay, and if I have written the G in this form in here, these are called the. These, remember, are basis vectors in cotangent space, okay? Corresponding to those, I have the tangent basis vectors in tangent space, which are just the partial differential operators. And the pairing between those is delta I dxj is just the pairing. It's just delta ij. What's meant by the pairing? The pairing is simply that each of these things being something in the dual space can be regarded as a function acting on something in the other space, okay? So then this acting on that produces a number for you, okay? That's what's called the pairing. The relationship between a space and a dual space. Yeah.
Is there a particular reason you're using Kronecker delta, or is that just to represent there's a number?
These are you can see that this satisfy this particular condition. If I have to go through all the systematic developments and so on and so forth. Okay, but actually, yeah. So this is called a natural basis because it depends on your choice of coordinates. Okay, and this basis is not an orthonormal basis. Okay, because when you use this metric tensor to calculate the scalar product, it's not the delta I, delta j need not be orthogonal to each other, not necessarily 0 if I is not equal to j. Okay. In fact, if you have two vectors, let me show you how it works. Now, these can be regarded as bases in the tangent space. So for a particular vector in tangent space, I can express it as something like that. You kind of think of this as a vector, basis vector, okay? But you don't write this, okay? The arrow over there, okay? And xi's would be the components of the vector with respect to this basis in here. So if I give you two vectors in here, let me write this as delta j in here, where both the I and the j are summed over, okay? Like so. And so G acting on xy would be like this thing acting on x and y, where you have one of those acting on one and the other one acting on the other, like that. Okay, and this would automatically making use of this relationship. And what do you get? G I j x I y j. Okay. And of course, this reduces to your ordinary notion of a scalar product if Gij were the Kronecker delta. Right? It's kind of like x dot y. The dot is given by the metric tensor. We knew this already, right? We talked about this many times in the classical mechanics course. If it was a Euclidean space, we use the Euclidean metric, which is delta ij. If this was a Minkowski space, we use the eta ij, and so on and so forth. But in general, for non-flat spaces, the Gij's would depend on positions, okay? So it would seem that the scalar product is actually in general depends on the position in the base manifold. So if you take a base manifold in here, right? At this point, I have my tangent space, okay? And so you got yourself two vectors, x, y, in this tangent space. And I can express each of those vectors in terms of the natural basis like this, okay? How do I calculate the dot product between those two vectors? Like that. Okay? All right? And so this since the Gij depends on x, right? Gij depends on the position, right? So the scalar product is something funny. The scalar product actually depends on the position in the base space. All right? That's one thing. Now, there's for Riemannian geometry, there's a requirement that the G has to be positive definite, which means that the scalar product of a vector with itself is always larger than or equal to 0. This is called the positive definiteness property of the metric tensor. But obviously for the Minkowski space, this property is not obeyed, right? Because in the Minkowski space, you have a situation where the scalar product of a vector with itself may either be time-like, light-like, or space-like, so it either be positive or negative or 0, okay? But let's consider this case. Actually, we don't need to make use of it, but for Riemannian geometry, this is understood, the positive definiteness of the metric tensor. But much of the things that we are going to be talking about will apply also to the relativistic case where you do what is called a pseudo-Riemannian manifold instead of a Riemannian manifold. Okay? pseudo-Riemannian. Okay. Okay. And so, given a metric tensor, then then the length of a vector is then, of course, defined to be the square root of gxx, right? Whatever that gxx is. If it's positive definite, you can take the square root, okay? And then that's defined to be the length of a vector in Riemannian geometry, not pseudo-Riemannian, okay? Riemannian geometry, okay? Furthermore, in this case, you can also define the angle theta between those two vectors. And how would you define it? You define it exactly the same way as you would for an ordinary scalar product case, okay? Which would be x dot y divided by the absolute value of x times the absolute value of y, okay? So, the cosine of that theta. So for any two vectors on Riemannian space, you would have cosine theta is equal to x dot y, which is g x y, divided by length of x times the length of y, where the length of a vector is defined like that. Okay? So everything depends on the metric tensor G. Okay? And for Riemannian geometry, the gxy is always, let me see. No, gxx is always positive or 0, but gxy, need not be. Okay? It can be either positive or negative or 0, as a matter of fact. Okay? And furthermore, I think we have seen this already, that we have written that result down. You can use this metric tensor to calculate the length of a line segment, so-called arc length, of a curve between 2 points. So let's say in Riemannian manifold, you have a curve. The curve is parameterized by some parameter that we use the t, symbol t, to denote that. The time, for example, okay, t0 to t1. And as the variable t varies from t0 to t1, your point moves along the curve like this. That's called a parameterized curve. And you specify that by giving what? By giving all the coordinates as functions of the time t. Okay? That's called specifying a curve by means of a parameterization. Okay? The shape of the curve itself is independent of the parameterization. But the speed with which you go along the curve obviously depends on the parameterization. Okay? But we are not worried about the speed at this point, since, let's say, we are just worried about the length of the arc length. And, this is also, ds squared is gij dxi dxj. So I'm ignoring this little Cartesian product thing in here. Okay. And so that ds itself is the square root of this. Okay. And ds is apparently calculated by integrating, like so, from 0 to t, and now you divide and multiply by dt. And you put the bottom dt inside the square root, so it becomes dt squared. Like that. Okay? And so it becomes a time integral, right? So this is from point 0 to point 1. You integrate from time 0, t0 to t1. And you can imagine being able to do that integral because you are given the parameterized curves, you're given the parameterized curve, so therefore you can differentiate all the coordinates with respect to time. And also the g is given in terms of the x's, but all the x's are known as functions of time t, so the whole integrand is a function of time t, then you can imagine doing that integral, okay? You've seen this many times already, right? And so this is the length of a curve in here. And now we'd like to show you that the Gij is actually a tensor, a rank 2 tensor, which means that it has to transform like one. The kind of transformations we are talking about now is not a frame transformation, but a general coordinate transformation. A general coordinate transformation, like when you go from a set of local coordinates x1 to xn to another set of local coordinates x prime 1 to x prime 1, where the direction can go both ways, so that all of the x primes are differentiable functions of all the x's, and all the x's are differentiable functions of all the x primes. Okay, that's the kind of transformations that are of interest in general relativity. You're talking about they're called diffeomorphisms, okay, which means differentiable both ways. Or physicists just call them general coordinate transformations, right? And so you would expect that the transformation matrix would be a Jacobian matrix, okay? dx prime by dx, okay, ij, and so on and so forth. Transformation matrix would be a Jacobian matrix relating the x primes to the x's. So how do we verify that the g's are transformed like a tensor? Essentially, we would have to verify this relationship that now the g's are fields now, right? These are tensor fields. These are not tensors at one particular point. These are tensor fields. So we would have to verify a relationship like this, that if you go from a set of coordinates x to another set of coordinates x primes, the shorthand for x1 through xn to x prime 1 through x prime n, you would expect that if G were a tensor, that G prime ij, when expressed with respect to x prime, would be related to the same G when expressed with respect to x in some way. And that transformation would be dxk dx prime I dxl dx prime j. Okay, this is like a Jacobian matrix. Okay, it's like a Jacobian matrix. You know, in this particular way of writing this, which are the x's on top, okay, and which are the x's in the bottom. The ones in the bottom must be prime, because you can imagine that when these primes go on to here, it becomes the x prime also. On the right-hand side, if you just get rid of these, that would be just the x's like that. Okay? So it transforms like a tensor. So this would be like GKL. This would be like some transformation matrix, which you can call AIK. This would be AJL. You see? Okay? Except that all these are functions. Okay? So if you define AIK to be this, then you would have a transformation rule which looks like this. G prime IK x prime would be equal to AIK AJL GKL x. Compare this formula with the formula that I gave in chapter 1 of your classical mechanics book. It transforms like this. Okay, so then G is a tensor. Now let's prove why this is so. In fact, it's quite simple. This rests on the fact that whereas G is a tensor, the arc length squared must be an invariant. Okay, the G depends on the coordinates, but the arc length squared does not depend on the coordinates. Okay, so we can write a formula like this. Now in general, ds squared must be equal to Gij x dxi dxk. Okay, but if you use the other set of coordinates, this must be equal to G prime ij x prime dx prime I dx prime k, right? And the two must be equal to each other. Okay? And so we have, getting rid of this, we have this is equal to that. All right? Now, what I just have to do is to then write let me write this, instead of ij, I'm going to call it KL. because they're summed over the dummy indices. Okay, so I have that, and therefore I have GKL is equal to, let's start from this side, okay, and I'm going to write this. What I want to do is to express dxk and dxl in terms of dx primes. That's easy enough to do, okay? So this is equal to gklx. Dxk can be written as partial xk, partial x prime. Here goes the summation index, which I'm going to call I dx prime I. Is that okay? That's for the first one in here. Okay, because all the xk's are differentiable functions of all the x primes, okay? It's just like a, what is it called, a chain rule of differentiation, okay? So that's dxk, right? Similarly, I can write dxl as dxl, dx prime. I'm going to have to use another index called j, dx prime j, okay? In other words, well, you already see the result, right? So you just put this together with that dx prime I, dx prime j. I can write it elsewhere. dx prime I, dx prime j. Sorry, this is j in here. Ij assumed, okay? And therefore, you have g prime ij x prime, which is the coefficient of dx prime I, dx prime j, must be equal to all that stuff, which is the coefficient of dx prime I, dx prime j. That's precisely this formula in here. Okay? So that's how you show that the g is indeed a tensor, transforms like a tensor under general coordinate transformations. All right. Next thing I'm going to do, I'm going to show you the origin of the raising and lowering of indices, which you have perhaps become quite used to. You know that, and this has to do with, you know, things in a vector space and then things in a dual space. Now, so the G introduces a scalar product, okay? A scalar product, let's say this is a vector space, right? Two vectors x and y, vector space V. Once you're given a vector space V, you have another vector space called V star, which is the dual space to the original vector space, so that you can pair up things in here and here. You take one thing in here, pair it up with a thing in here, you get a what? You get a number. Because the things in the dual space are supposed to be linear functions on the things in the original space, and conversely. In other words, you can take two things. There's something called x star, for example. Use something called z star, for example. Okay? And I can take z star and pair it with x. The mathematical notation is like this. And that gives me a number. And that gives me some real number. We're talking about real vector spaces. Okay? Well, here's the basic thing. And I think this I also discussed in chapter 1 of the classical mechanics text. Once you're given a scalar product in a vector space, then this gives you a one-to-one correspondence between vectors here and vectors over there. Okay? In this way, that gyx must be equal to yx star. In this sense, this is true for all y in the original vector space, okay, and x and a particular x in the original vector space, there exists a unique x star which corresponds to x such that this is true. Okay? And you can prove that it's unique. Okay? So part of what the scalar product does for you is that it associates direct one-to-one relationship. It gives a direct one-to-one relationship between things in the vector space and things in the dual space. Before you introduce the scalar product, there's no such relationship. Okay? I mean, you can pair something here with anything in there, but here something in here directly corresponds to a unique thing over there, in such a way that this is true. Yeah.
Could you repeat that last line about the dual space?
Once a scalar product is given, it allows you to associate some vector in here with a unique vector over there by this relationship.
But then what about the opposite of that?
Opposite is also true.
Okay.
Once you can associate one-to-one, then something here is directly related to something here. Okay, so one-to-one, one-to-one. Okay, a specific one-to-one way. Now, perhaps you remember in quantum mechanics, some of you have taken, none of you have taken quantum mechanics, you use the Dirac. Have you seen this notation? Bracket notation. Okay, bracket notation. This is something in the original Hilbert space. This is supposed to be something in the dual space. The bra vector is in the dual space. The ket vector is in the original Hilbert space. Okay, you can read this as either pairing in that sense or a scalar product. Okay, because of this uniqueness, correspondence. Okay, like that. Okay, now let's try to do something like this. So, corresponding to x, some x, I have xi di. I write that like this. And now let's try to write the corresponding vector in corresponding to x. I will have a unique x star, right? Given a metric, given a scalar product. And you see the basis of this being in the dual space to this one is the dxi. These two are dual relationships to each other. Okay, and this is an upper position, so I have to write this as a lower position guy, x sub I like that. X, you see, that's why the Einstein notation is useful. Okay, repeated is always summed over. If this is up, then if you want to sum it over, the other guy must be down. If this is down, the other guy must be up if you want it to be summed over. Okay? And so then, you can then use this notation and directly confirm that if you start off with some upper index thing in the original space, then the lower index thing must be equal to this because of the g involved in here. Okay? And that's how we told you to lower indices, right? That's how we told you to lower indices. Sum over the j that gives an I over in here. You can directly verify that from there. Okay? Similarly, you can raise an index also by using g upper ij. So xi is equal to g upper ij xj. The g upper ij is simply defined to be the inverse of g lower ij. Now, one of the properties of the metric tensor is that it's non-degenerate, which means that the determinant is not equal to 0, which means that the inverse must exist. Otherwise, it's no good as a metric tensor. Okay? So once you're given any g lower ij, which is the original metric tensor, you must have the corresponding inverse, which is simply in either the physics literature or the mathematics literature is written as g upper ij. So it's a 2-0 ranked tensor. Okay? And so that's why, because of this thing in here, you see, raising and lowering indices involves the metric. That is the reason behind why raising and lowering indices involves the metric. When going from something in the vector space to something in the dual space, you either raise or lower an index by the metric tensor because of that. Okay, let's stop here.
So this is lower, when it's raised upper, when it's raised lower,